Hello everyone. My name is Shirali Zakwan, and today I'm going to present the paper OpenDialKG, Explainable Conversational Reasoning with Attention-Based Walks over Knowledge Graphs, um, authored by this team of researchers from Facebook AI, consisting of Seung-Hwan Moon, Parag Shah, Anuj Kumar, and Rajan Suba. And yeah, let's get started. So these are the outlines of my presentation. We first try to take a look at the introduction, which consists of the problem motivations and also the main contributions of this paper, and then straight into the method, which is called the DialKG Walker, like an encoding and decoding scenario of the model, and then the dataset, which is owned also by this research team called OpenDialKG, and then finally the empirical evaluations, the baselines that they use, and the results of their proposed model compared to baselines, and also the conclusions that we can take from this research. And for the first one, going into the introductions, I want to sort of introducing the problem that that motivates the author to study this research. So if you're talking about an open-ended dialogue system, we want our model to understand, of course, the conversational context, but more importantly, we want our model to also respond naturally and introducing um, relevant entities so that it can become informative to the user. So let's say we are talking about movies or books, and we want to know the newest ones, and we talk to chatbot. We want the chatbot to give us informative, probably movie titles or book titles that we are most likely to be interested in. And the challenges here is because the domain is like there are so many domains. So if we want to make like a domain agnostic chatbot, it will be pretty much challenging because of the scale of the facts, because there are just so many facts and entities out there, and we want to have like a scalable prediction to support our chatbot. And this problems motivate the authors to study a model that can map dialogue transitions or dialogue context into the knowledge graph, like the corresponding knowledge graph, so that it can identify like a subset of ideal entities to be mentioned or to be informed to the user. And this is the one of the example of the study. So you can see at the top half of the picture that is the dialogue between a user and the chatbot. So here we are talking about a book. So first, the user wants to know books, sort of like The Catcher in the Rye, and then the chatbot replies by asking more questions. So do they want, or do you want prefer? Sorry, do you prefer books by the same author or same genre? And and then the conversation goes on. And what basically happens here is that whenever the chatbot receives like entities from the user, in this case, the first one is the catcher in the rye, it will like sort of traverse the knowledge graph starting from the seed entity, the catcher in the rye, and then try to take a look into all the relations, like probably is a relation, which is we can say that the catcher in the rye um, is a book, obviously, but also it can be part of is a relation. So, for example, this catcher in the rye um, has the American literature genre, so it is represented by this sort of is a relation or is a age in the graph, and this model will take advantage of those information and then use that uh, as a part of their replies so that it can engage a good conversation. And then it goes on, goes on, goes on, and finally it can recommend the other book, which is in this case the Nathaniel Hawthorne novel of Scarlet Letter. And basically it's just the matter of um, traversing the graphs efficiently, so you don't have to consider all the possible entities, but just the right ones, or the um, or in the other hands, or in other words, basically you have to prune the non-ideal facts, even though it's correct, but it's maybe not as relevant as the other. So that's just the main problem, or the main um, point of this paper. So there are three main contributions of this paper. The first one is the decoder itself, the graph decoder. which will traverse a very large common sense KG consisting of 1.1 million facts and over 100K entities. And the second one is the involvement of this zero-shot learning. So basically, after we traverse the graph, we'll end up with many entities that we can obviously mention to the user, but then we want to pick some that are relevant, right? That are consistent with the dialog context. So this is where the zero-shot learning model plays. And then, yeah, hopefully by using the zero-shot learning model, we can re-rank our entity candidates and give the best ones to the user. And finally, to support this study, they also create this new parallel open-ended dialog to KG corpus called OpenDialKG, which is basically a pair of two things. The first thing is the dialog itself, and the second thing is the ground truth KG path that is relevant to the dialog. So, for example, here the below KG is just like a small part of the whole KG, which is related to the dialog. So it is what they annotate basically. And moving on to the method, so here are the high-level summary of the model, the DialKG Walker model. So it takes three input, as we know, the set of KG entities mentioned at the current turn. So for example, the first turn, they take into account the catcher in the right entity as their shift entity. And then it also takes the full sentence. So basically the full sentence is this: can you recommend any classic book like Catcher in the Rye? And then also the dialog context, which is nothing in the first turn because you don't have context at the moment, but then for the subsequent turns you will have dialog context, obviously. And then for the decoder, I would say it's pretty much basic decoder in which in each decoding step you will have a new entity and a new relation to explore in the graph, and it's sort of like generating a walk path um, for another module to take into account, and after this other module take into account this walk path, they will use this zero-shot KG embeddings or zero-shot learning model to pick the most relevant, the best entities consistent with context to give to the user. So there are basically, I would say, three steps basically. So the first step is taking three inputs, and the second step, the DialKG Walker will generate some entities and path, and then the third step is this other module will take into account all those generated entities and pick ones that are most relevant using the zero-shot KG embeddings. Basically, like ranking mechanism, as you probably see in other papers. And here are the picture of the architecture of the model, right? So the left ones, the input encoder, will take three things: the initial KG nodes or the initial KG entities, in this case the Romance and DiCaprio, and then the utterance, for example, recommend me, and the dialog context, whatever it is. And for the initial KG nodes, it will be converted into factors using the KG embeddings. And then for the utterances, it will be converted into some fixed size vector, and that also is the same with the dialog context. For the dialog context, they use the attention by LSTM architecture to convert it into a factor. And then these three factors, or two perhaps, because the utterance and dialog context will be combined into two factor first. And then this two factors, the textual factor and the entity factor, will be inputted into the modality attention, which basically assign like attention weights to each component, which one we should pay attention more to. Is it the entity? Is it the utterance? Is it the dialog context? And then it will be given into the DialKG, which will treat it as a set entity, and then they will just traverse the graph, and it will produce two things: the entity itself and the path or the set of relations that are being traversed. And also, while traversing, they also put attention or compute attention over walkable paths. So each path or each edge or each relations will have its own attention. And then finally, after we gather all the entities, we will apply the zero-shot relevance to re-rank our candidates. In this case, there are Titanic, Drama, Kate, Cameron, etc., etc., and then we use the top ones to be given to the user. Also, the other module that I've previously mentioned above is called the entity re-ranker. And then moving on to the notation. So I'm going to tell you about these notations because it is beneficial before we dive into the more detail. So the knowledge graph is notated as TKG, graph of knowledge graph, which is consisting of the vertices and the relation. And this relation is kind of like ages in normal graph. And then this relation will have two other notations, the capital phi r of phi, which basically says the neighbor of vertex phi small that are reachable through this relation r small. And the other one is phi capital R capital N of phi, which says or which denotes also the neighbors, but those who can be reached not only just with one hop but with n hops, right? And the R capital stands for all the relations that is used within the hops, or basically just a set of relation within the n hops you take. And then for the input output, first we want to talk about the X input, which is the triplets, as you might expect, triplets of entity, sentence, and dialogue context. And for the output, denoted by Y, will be two things here, the entity and R, the relation. So not only the entities, but also the path that we take to arrive at those entities. And for the latest row here, so basically xe to the I means that means a specific entity within the entity set that you have gathered at index I, and that goes the same with ye to the I. And for the ye to the I t blah blah blah, it is basically I think if I remember correctly, let me refer to the paper a little bit just to make sure that I get the understanding right. So here, yeah. So we know that ye is the set of entity paths. So ye ye to the I from T1 to T capital basically says all the entity path, not all the entity path, but if the entity path has length T capital, then ye to the I at T1 means that it is the first entity throughout those paths, and then we go on until the capital T paths. Yeah, that's what it is. Okay. And then next we go into the task formulation. So it is pretty much the same as any retrieval formulation. So you have first to create a function with learnable parameters that projects inputs samples, which is the X, the entities, not the entities, but all the sub entities, sentence and dialogue, into the same space as the output representation Y, which is the entities and relation. And then you score it, meaning that you will have some kind of matrix between the predicted ones and the ground truth, right? And then you just take an arc maximum over all those stuff and pick any entities, any Y entities, output entities that are have the high score basically. And this is and other notation is the phi of xe, which is saying that which means that you only consider entities or Y that are the neighbors of the direct neighbors of xe basically. And after we know the notation, I want you to take a look or learn a little bit about the input encoding, which is again consisting of two things: the entity encodings or entity embeddings, and then the sentence embedding and also the dialogue embeddings. So first we talk about the entity embeddings. So for the entity embeddings, they use this kind of mechanism to compute it. So they have this indicator function that takes into account two things or two entities, as and O, as is a subject, O is the object, and it will output 1 if it's a valid relation and 0 otherwise. And they do it by using three functions here, three but one function actually. So E, the function of basically just a table lookup to extract the embedding from entities. And then they will use some kind of score that is in the actual form of this score function is a DNN. So this DNN take the triplex of sentence, relation, and object embeddings. Sorry, not sentence, subject, entities, relation, and object entities embeddings, and then feed it into the DNN, and you will have some kind of score. So we use this basically to have a embedding of triplets basically. So just to make sure, to make it clear, we have embeddings for each entity. We have embedding for S, for R and O, but we also want to have embeddings for a triplet basically, and this is the way they do it. And the next one is the sentence embedding or sentence representation, which basically adopts from other papers. They use this attention-based BiLSTM to represent the textual context of surrounding words. And they also use this pre-trained word embedding growth, which also is taken from other paper. And the dialogue representation or dialogue embeddings are computed a little bit different. They use another method from another paper called hierarchical BiLSTM. So I guess they take different route here because when you talk about dialogue history, you have several several sentences, and you might want to treat each sentence differently. Like you want to weight like previous sentence more than the other sentences, right? Like the direct previous sentence, and that's probably why they use this paper, this method. And by the way, this method also use self-attention into account, like taking self-attention into account. Okay, I think that's all about the encoder, the input encoding. Then we move on. We now talk about the decoder. So when we talk about decoder, we want to talk about the loss, like what is it trying to optimize basically. And here are two things that is being optimized in the decoding step. So the first one is the basic supervised loss for generating the correct entity, like probably any other decoder will do, like any other decoder would do, just a simple supervised loss. And then the second one is the one that is I would say novel or a little bit different. It's called walk loss. So not only you have to generate a correct entity, but also the optimal path. Like you have to arrive at those entities optimally, and that's what this walk loss accounts for. And they also use this a simple weight decay regularization to compute this loss basically. And this is what I've been talking previously about the re-ranking. So this is the formula that they use for doing re-ranking using this zero-shot relevance score. So this is no other than the supervised hinge rank loss basically. So you want to take either 0 as your loss, or the difference between the margin and your prediction. So before talking about the margin, we want to talk about how they actually do this. So they use a so-called negative sampling. So instead of only having a ground truth or the positive sample, you also want to have the negative sample as comparison. So there are two things that you want to optimize. The first one is how do you get a prediction that is close to ground truth, but also quite a bit far from the negative sample. So that's what they're trying to do here. And the way they do this is basically using this supervised hinge loss. So you take the margin by conducting dot product between the y hat to the y e to the I. So y hat is the negative sample, y e to the I is your correct sample, the ground truth. So that's the margin. And the margin will be subtracted by the dot product of both the prediction, the f of x to the I, and the ground truth, and also the negative sample. So yeah, so I said before, this particular particular dot product of f of x to the I times, or dot product to the difference of y to the I minus y hat is supposedly doing the objective, which is to produce higher dot product similarity with the correct label than with random incorrect negative label. And that's it. That's the way they compute it. Okay, so I think I want to skip this one because I've mentioned this over and over, and just going to talk about some more details here. So regarding the decoding step, it uses attention. So basically, when I explore um, the graph, let me go back to the to the first slide, this one. So whenever they want to traverse, like say from the catch and the rye to the next entity, you have here four or six. I think it's four. I don't know if the blue edges count or not, but say it is not. So let's say or it is. Okay, I think it counts. So let's say we have like six edges here, the two blues and four blacks. And whenever they traverse, they try to calculate attention. So which walkable path or which walkable edge is weighted the most, etc., etc. So um, that's what these equations um, these equations are trying to do, basically. So if you take a look at the equation 6, this is the like the most common stuff that that you see if you are if you are um, reading papers regarding decoder, regarding tension. You have the I, which is the input. You have the CT, which is the context or cell memory in RCM. You have the O, which is the output, and HT is the hidden state. But I'm not sure if I can explain it to you per symbol because it's not explained in the paper clearly as well. But just so you know, this is the normal equation that you see when you're into decoding paper or when you're into some kind of attention paper. And the most important symbol here is the ZT. ZT is an entity context vector. So yeah, so that the ones that we get from the KG embeddings basically at decoding step T, and then we try to basically update the CT values to produce like a decoder output, right? As the normal decoder would do. And the attention is symbolized by this alpha T, which is then used to update the ZT. So the ZT will be the sum of the previous hidden state, HT minus 1, plus the weighted sum of all the relations, like the possible relations, the walkable paths, against its attention weights, basically. So whenever so there's nothing novel from this decoder. It's just the same as other attention-based decoder, which you update your ZT using your hidden states. Also, the sum of the weighted sum of attentions, basically. Let me know if you find this a little bit overwhelming, but because I do at first. So this is I think this is a little bit enhancing what I've said before. So we know that previously the decoder loss is this one, right? We have the walk loss. So again, the walk loss will be divided into two things here: the loss of entities and the loss of relations, because we have two outputs, as I've said before, the YE and YR, YE for the entities, YR for the relations. And then finally, the path ranking. I think this is one of the most important equations in the paper. The way they actually re-rank the candidates, right, in the final equation, sorry, in the final step. So so they don't so they previously said that they use a zero-shot relevance model to compute the score to re-rank, right? But actually, after I take a look deeper, they don't only use the zero-shot relevance score, but also the self-attention based output. So the left one here is the zero-shot relevance score, which is computed through hidden state, basically. So the final hidden state will be dot producted with the YE to the I, which is the ground truth. No, is it the ground? Yeah, sorry, yeah, which is the ground truth of the label. And then you will wait, no, it's not the ground truth. It's your prediction, I think. Yeah, it's a prediction. So we have two outputs here, right? YE and YR is our prediction. So YE to the I is your predicted entities, and then you will be having a dot product between those and the final hidden state of your dial KG. And then you take the arc maximum. No, sorry. Let me get this straight. So first you compute the dot product within the hidden state, like latest hidden state from the LKG. against the entities that you get, that every entity that you get, right? And then you sum it with all the relations, the YR corresponding to your current entity that you are trying to observe, right? With the attention weights and also the relation embedding. So RK here is the relation embeddings. Okay, and that's for one entity. So you do dot product between hidden state and one entity, and then you sum it with with this weighted sum of all the relations corresponding to that entity. Okay, and then you do it over all the entities that you get in your prediction, and then you take the arc maximum of it, and the one that goes to the top is the one that you pick for um, for your user, basically. Okay, sorry if that's too complicated. How do I explain it? And then finally, this is the latest method or latest equation that we will see. It's for the adversarial transfer learning, basically. So the author has the idea if that if the domain labels are available, say movie, book, or sports, like beforehand, we can extract transferable features and learn optimal paths conditioned on domain embeddings. And basically, they want to utilize this idea to say that their model can better generalize over multiple domains. So they don't actually implement this or whatsoever. They just want to show that using this method or scenario, they want to show that their model can generalize an open domain, basically. And I'm not sure what is this entropy is, but I guess it's something related to the domain embeddings that is mentioned because it's not um, clearly explained in the paper, in my opinion. Okay. Okay, that's all about the hard stuff, the method equation and stuff. Now we're talking about a little more yeah, light stuff, I should say. So about the dataset itself. So this OpenDialKG consists of 90K turns across 15K dialog sessions, meaning that for each dialog session you will, in average, have 6 turns, right? And it's going to be paired with the corresponding entities and relations in the KG, as I've said before many times. And these dialogues were generated in the settings of Wizard of Oz, which I believe is mentioned and explained in the previous previous meetings that we have here in the class. So basically, it connects two crowd workers to chat, and then the first agent will be given a set entity, um, say say football club, and then the second agent will be provided with a list of facts relevant to the entities, say Liverpool Football Club, Chelsea Football Club, or Man United Football Club, for example. Then they choose the most natural and relevant facts in their opinion, and then this loop will be, this process will be looped until the goal is met or either of the agent decided to end the conversation, basically. And this one is the domain distribution of the OpenDialKG. So OpenDialKG is, I'm not going to say open domain, but it indeed consists a good amount of domain, movies, books, sport, music, etc. And they divide it into two tasks: the non-task oriented task, which is the chit chat one, and the task oriented one, which is the recommendation. And for the recommendation, they have movies and books. For the chit chat, we have sports and music, which kind of makes sense because when you talk about movies and books, you pretty much want to get a new movies or books to enjoy. And for the chit chat, sports and music seems relevant because when you talk about sports, you talk about like some things, but you don't really want the chatbot to recommend you some sports or whatever. Then the distribution here is leading towards the recommendation task with approximately, like, I would say 3 times. The recommendation is 3 times larger than the chit chat task, like in the terms of the data that it has. Okay. Then we're moving to the way they built their knowledge graph. So it's actually just taken from an available one called FreeBaseKG from Buzz et al. 2014. But they actually do some kind of post-processing. So they filter the tail entities. So the ones with low prominence scores will be disregarded. And this results in 1.1 million fact triplets over 100K entities and 1.3K relations. And finally, it is divided into train, which is 70%, validation, which is 15%, and test, which is also 15%. And yeah, I think the task formulation you all get like the gist of it, so I don't want to repeat it again. But the important thing here is that this paper is not focused. It's not focusing themselves on the way you generate the sentences, or not focusing on end-to-end generation, basically. But instead, it only focuses on a specific task called the conversational reasoning. So the way the chatbot reason, the way the chatbot thinks about entities to mention, basically. And the paper tried to make it scalable, make it you know deployable, I should say, because it involves a quite big knowledge facts base, which is consisting of 1.1 million facts, and those will not be um, like those data sets, those knowledge graphs with that size will not be able to be processed if not for an effective way to decode the graph. Basically, that's what the author trying to solve. And for the baselines, they use three baseline here. So the first one is the famous seek to seek, but the only not the only, but they actually tweak a little bit. So the softmax layer is disregarded and they replace it with a zero shot learning layer for re-ranking, basically. So it's more suitable to their needs, but the other things remain the same. And for the trial STM, the second baseline, so a little bit about trial STM. It is a method that will encode each utterance and all related facts within one hop. So this is a method that are already involving knowledge, in fact, right? But only within one hop. So the next immediate entity after the seed entity, right? And they work like using some retrieval, so it's not fully like abstractive. So they retrieve from a small predefined KG facts, n equals to 10, which is actually also a modification from the paper, from the author, because originally in the paper, in the trial same paper, they use sentence bank, but here, because the problem is more leaning toward entities, they replace the sentence bank with the predefined KG facts. And finally, for the third baseline called extended encoder decoder, this one is pretty much playing on the input. So you will, I know what is the exact method, but probably something like concatenating the knowledge factor with the actual textual input. But the rest of the architecture, the seek to seek architecture remains the same. So it's just conditioning the response generation with this knowledge factor input. But the drawbacks from this method is that it omits the structural information from KG, which is proven beneficial, at least from the author's perspective. And lastly, they also conduct experiment using three configurations to examine the contribution of each component, the entities, sentence, and dialogues. So the first one, like the proposed one, will have all of those. Then the second one will exclude the history, so only entities and parent sentence. And finally, the ones that excluding any textual context, so only the entities. And here are the table, the result table. So the first one, or the first comparison is for the in-domain scenario in which you train and test in the same domain. Here we have the all domains to all domains and movie to movie. And we can see that even the one with only entity, the DialKG Walker with only entity can overperform some of the baselines. But ultimately the one with all the stuff, the E, S, and D, the proposed one overperforms all the baselines, with quite a fine margin, I should say. So the most close one is actually the normal seek to seek from Subskifer. But yeah, but still, it is overperformed by the DialKG Walker. Typically for the movie to movie, but we can see here that for the all domains to all domains, the seek to seek is kind of close to DialKG Walker. It's just losing much in the R at one, or the recall at one position. Sorry, the recall at one matrix, which is only 3 against 13.2. But when we talk about recall at 3, recall at 5, it is quite close um, to the DialKG worker. And then this one is for the cross domain, so train on one domain and task on another domain. But it's not like a very it's not actually a simple one. It involves like some kind of transfer learning method that I will talk about in a later section. But for this slide, for this particle table, I just want to show that the proposed LKG worker also performs the other baselines with a quite fine margin. And finally, the third method, or the third type of evaluation, is through human. So this one is basically saying that if, not if, but basically the metric is the percentage of cases chosen as top care response by the raters. And again, the KG worker overperforms all the baselines. And we see also the similar patterns here. The closest one is the Suscover, or the C2C, in which if we increase the K, it becomes, the difference become more, more subtle. 37.1, sorry, 33.1 against 36.3 for K equals to 3. Okay, this is what I've talked about earlier, saying that it involves some kind of transfer learning to do the cross-domain one. So there are two things here. So the first one is called TLADV, or TL, or transfer learning adversarial, which is shown by the red line. So this transfer learning adversarial is basically different from the common transfer learning that you might know. So the common transfer learning that you might know is through fine tuning, which is the blue line, the TLFT, which basically, as you all know, we pre-train on some domain and then we fine tune on the other domain, but that's actually not as good as the TLADV for this dialog case. So TLADV is some unique transfer scenario, in my opinion. So instead of having like two steps, like pre-train and fine-tune, you actually utilize both of the data, right? So you ended up with almost 2 times the size of your original data, right? So let me refer back at the paper so that I can explain it more clearly regarding this TLADV. Oh, so yeah, so the main thing here is that you will have like some sort of like discriminator that differ between the source and target domains, but ultimately you train in one step, but it's just some kind of, I don't know, maybe label or some seed or something that can differ. Oh, this data is from the source domain, this data is from the target domain, but you train it in simultaneous way, so you train it at once basically, and it is proven to yield a better result compared to the to the traditional transfer learning scenario, which is the fine tuning one. And finally, it's just the error analysis. So let's take a look at least in two examples here. So the first example is about football, my favorite topic. Yes, I believe Thomas Müller, has played in Munich. He also won the Bravo Award. I think that's awesome. And we can see that actually the GT, sorry, not the GT, the ground truth is the position of the player. Thomas Müller is a forward at Bayern Munich, um, and that's what is being expected. But both of the model, the KG Walker and the baseline of extender encoder decoder, didn't really yield anything useful here. Lionel Messi is obviously some different player, so KG Walker like sucks in this case. And also extended encoder decoder says Mueller, which is actually an entity that has been set in previous utterances, which also doesn't give anything useful. So both model fails in this case. And the second one is where the KG Walker has an advantage over the baseline, or over the extended encoder decoder. and it correctly predicts that it is like Raman's genre of book by Mark Overstall. And in contrary, the extended encoder decoder says that it's just a book written in English, which might be correct, and which is correct in fact, but it is not. So this is what I'm trying to say in the earlier slides, saying that we want to introduce the not only relevant but also natural and engaging entities. So if we say that if a chatbot says it's a book with English as a language, it might be correct, but it's not something useful, something engaging for the user. But if we say, or if we can understand that this book is something um, with romance as the theme of the book, then it might yield a more useful and engaging conversation rather than if it only understands that it is a book written in English. Okay, so I think that's all for the slide. Because I think it'll be too much if we talk about all the example. Okay, we arrive at the conclusions. So again, to sum it up for the topic, the author basically studies conversational reasoning grounded on knowledge graphs so that the model can navigate through large-scale KG effectively, pruning non-ideal or non-engaging entities, basically. And for the data set, they credit themselves to support the study. It collects a so-called OpenDialKG, a parallel corpus that maps between dialogue to its corresponding knowledge graph, like a small part of knowledge graph um, dedicated to the dialogue, to a certain dialogue. Okay, sorry, I'm having an issue with my internet connection. Um, Give me like a couple minutes before I resume. Okay, so the next conclusion is about the model itself, the DialKG Walker. So this one improves over the state of the art, like the baseline before, like the tree baseline before, um, by utilizing two things. The first one is the attention-based graph decoder. I wouldn't say it's novel in terms of decoding stuff, but since it involves like the optimal path loss, the loss considering the optimal path, yeah, you can say it's novel, but in terms of decoding step, it's the same as any other attention-based decoder. And second one is the zero-shot learning model. This is the one that is novel in my opinion because it like introduces one way or another way, new way to rank your entity candidates, which is pretty much novel and interesting to read and to understand. And finally, for the results, they conduct several kind of experiments, the in-domain, the cross-domain, and also three types of transfer learning, the adversarial, the fine-tuning, and no transfer learning at all. And the results from those experiments show that this model shows the model efficacy for the open domain or domain agnostic conversational reasoning. Okay, I think that's all for me. Please let me know if you have any questions. Yeah, cheers.